All right, so we're going to take a look at phase change graphing. So we're going to graph the energy in an object as its temperature changes. Or what we'll really do is we'll graph how the temperature changes in relation to the amount of energy being added in. So as you add heat into a substance, its temperature generally increases. During a change of phase, however, the energy that would usually force molecules to increase jiggling or vibration instead goes into breaking the bonds of the solid or liquid, the electrostatic force. Since the thermometer doesn't move during a phase change, the energy added during these phase changes is sometimes called latent heat, hidden heat. On the graph below, we're going to chart the temperature of 1 kilogram of water, starting at minus 30 degrees Celsius ice, and as we add energy for it to become steam at 120 degrees Celsius. Okay, so the temperature of this is going to depend on the amount of energy added. So we've got a graph that we're going to build. We are going to answer the following questions and then graph them above. So on the vertical axis, we want the temperature in degrees Celsius from negative 30 to 120. Now I've designed this so that it fits perfectly. So we've got ourselves the temperature, degrees Celsius, starting at negative 30, negative 20, negative 10, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. We don't need to add in any more numbers. Now, the temperature depends on the energy we add. So on the horizontal axis, it's not energy total, it's energy added. Okay, so we're going to label this axis energy added. Right? Because even when the ice is at minus 30 degrees Celsius, it has an energy. The molecules of ice are vibrating. What that energy is we don't know. We could calculate it. But we're going to add in energy and see what happens. So energy added, we have to add in, and I'm just giving you this number already. Well, heck, let's compute exactly how much energy we do need to add. Now this is our chart. We're going to need a workspace. Got myself a workspace right here. Let's graph what is going on. Let's build a timeline. We start, and you know what? I'm going to go up and down. Our starts at the top. We start off with ice, minus 30. We go down. We become ice at 0 degrees Celsius. Then we do a phase change to become water at 0 degrees Celsius. Then we increase the water's temperature to become water at 100 degrees Celsius. Then we do a phase change to become steam at 100 degrees Celsius. Then we do another temperature change to become steam at 120 degrees Celsius. Okay. Alrighty then. Now, we're going to identify there's 5 stages. We're going to have to use the formula 5 times. Our first one is going to be a Q equals MC delta T because there's a temperature change. Now, I'm going to write down, we know our mass is 1 kilogram, right? So our mass is equal to 1 kilogram always. That's easy. And then for this one, we're going to use our Q equals MC delta T. So we need to use our 4.18 is equal to C. Then for number 2, that is a heat of fusion. And we have to use our water at 334. I'm going to write it in green. Heat of fusion, 334 kilojoules per kilogram. Then we have water again. I just want to see something here a little bit. Ha 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 ha. I was wrong, as I often am. For our first one, ice is different than water. Ice is at 2.16 right here. So our first one, we don't use 4.18. Because it's ice, we use 2.16. For our water, we use 4.18 for our C. Then we have our phase change, and this is vaporization. So we add 22.56. Heat of vaporization is equal to 2256. And our last one is steam. To go from 100 degrees Celsius to 120 degrees Celsius. So let's look. Here's water vapor, 1.87. So we do C is equal to 1.87. Okay, now let's start working through these. Our first one is a temperature change. So we use Q equals MC delta T. And Q is equal to 1 is our mass times 2.16 times plus 30. Our temperature change is 30. And our Q is equal to, well, whatever that is. 2.16 times 30, 64.8. So we have to add in 64.8 kilojoules to get from here to here. You know what? So over here, beside this, I'm going to write the total amount that we've added, 64.8. This is the total so far. So to go from here to here, we had to add 64.8 kilojoules. Now, how much do we have to add in to go from here to here? Well, let's do that formula. Q equals M H sub F. Q equals 1 times 334. Q is equal to 334 kilojoules. So we have to add in 334 kilojoules to go from here to here. Now we've already added in 64.8, so now we just add 334 to that. To get to now, we've added a total of 398.8 kilojoules to get to here. So right, we added 64.8 kilojoules of energy to get the ice to ice at 0 degrees Celsius. We add another 334 kilojoules of energy to get to water at 0 degrees Celsius. And there's our total amount of energy added from the start. Now we got to go from water at 0 to water at 100. So there's a temperature change. So we use Q equals MC delta T. Mass is 1. C is 4.18. Delta T is plus 100 degrees Celsius. 418 kilojoules. So we added in another 418 kilojoules here. Which means up till now we've added in, to get to water at 100 degrees Celsius, we've had to add in 816.8 kilojoules in total. Right, we started at ice at negative 30. We added in 64.8 kilojoules of energy to get to ice at 0 degrees Celsius. We added another 334 kilojoules of energy to get to water at 0 degrees Celsius. We've added in another 418 kilojoules of energy to get to water at 100 degrees Celsius. Now we got to go from water to steam. That's a green one. Q equals mHV. Q equals, mass is 1 kilogram, 2256. I believe that's the number there, 2256. I wrote it kind of messily. I'm just going to check my notes. Yep, 2256. So our Q is equal to 2256 kilojoules. So we have to add in another 2256 kilojoules of energy to go from water to the steam. Now let's figure out our total. 3072.8 kilojoules. So to start at ice at negative 30 degrees Celsius, to get to steam at 100 degrees Celsius, we've had to add in 3072.8 kilojoules of energy. Now let's do our last one. Q equals mc delta T, right? There's a change in temperature. 1 times 1.87 times 20 degrees Celsius. 1.87 37.4 more kilojoules. So we've had to add in another 37.4 kilojoules of energy to take our steam from 100 degrees Celsius to 120 degrees Celsius. So the total $3,110.2. That's our total amount of kilojoules that we've had to add. All right, so now, in our energy graph, for energy added, well, we start at 0 kilojoules of energy added. Then we have to make it all the way up to about 3,100. So if we count up by hundreds, 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That gets us to 2,000 there. That doesn't work. 100 each. So let's go 200 each. That'll be 200, 400, 600, 800. There's 1,000 kilojoules added. Then 200, 400, 600, 800, 2,000 kilojoules added. Then 200, 400, 600, 800, 3,000 kilojoules added. Now let's start. And I'm going to do the temperature changes in blue and the latent heats in green. Let's start graphing. So when the ice is at negative 30, we've added in 0 extra energy. Then we added in, then you see we added in 64.8 kilojoules of energy, and we're now at 0. So 64.8. This is 200. This is 100. That's 100 right there. It's going to be like right there. Boom. It went up really quickly. Then we added in another 334 to get to 398.8. So that's up to 400. So we added in some more energy. We got up to 400. This is our latent heat. Right? This is our heat of fusion right here. We added in energy, but the temperature didn't go up or down. Then, if we look here, we added in another 418 kilojoules of energy, which took us up to about 800. We got all the way up to 100 degrees Celsius. So this is another temperature change one. So at 800 added in, we got all the way up to 100 degrees Celsius right here. Right, so that one that I just did was this one right here, from water at 0 degrees Celsius to water at 100 degrees Celsius. Then the next one, we have to add in 2256 to go all the way up to about 3,000 kilojoules. All the way up to 3,000, and our temperature doesn't change. This is our heat of vaporization. We have to add in a lot of energy to change from water to steam. And then our last one is going up to about 3,100, which will be right about here. And that takes us up to 120, so right here. So you can see this first one here was from ice, was all ice, minus 30 to 0 degrees Celsius. This first one, this first flat spot right here, was the transition from ice to water. And it took a little bit of energy, and you can see the temperature didn't change. This next one here, big temperature change. This was from water. This was all water at 0 degrees Celsius to 100 degrees Celsius. The temperature changed from 0 to 100. We have to add in that amount of energy. Then up here, this was the transition from water to steam. You can see it took a lot of energy to transfer our water to steam. That's why steam burns are so dangerous, because they have so much more energy than water. Last one. This was all steam, an energy change. The steam went from 100 degrees Celsius to 120 degrees Celsius. And we had to add in about 100 kilojoules of energy to do that. So this is a phase change graph for water. 1 kilogram of water. So phase change. It went from minus 30 to 120 degrees Celsius. All right, now, this is an interesting question at the end. Would the graph look any different if 0.1 kilogram of water was used instead of 1 kilogram? The answer to that is the graph would look the same. This scale, this energy scale, would be reduced by 1/10. So this would be 100 kilojoules. This would be 200 kilojoules. This would be 300 kilojoules. That's the only difference. All right, so you should be able to build a phase change graph like this. Thank you for watching, I guess.